Okay, last screencast for Mastering Physics problem set 6.1. I'm going to work through the coffee cup on the roof. An absent-minded person places their coffee cup on the roof of her car. Wow, it's a woman, absent-minded woman. Usually it's a man. She dashes back into the house for a forgotten item. When she returns to the car, hops in, takes off, cup is still on the roof. If the coefficient of static friction between the cup and the roof is 0.3, what is the acceleration, the maximum acceleration that it can have without causing the cup to slide? So we have to solve for this acceleration here. Okay? I'm not going to draw the whole car. I'm not that good of an artist. I'm just going to draw the coffee cup on the top here. Okay, there it is, steaming. And you know you're trying to solve for A, and they tell us the coefficient of kinetic friction is 0.3. So mu is 0.3. They did not give us a mass, and that is troubling to some of us. So the car is, we'll say in this way I've drawn it, I'm going to say it's accelerating in that direction. If you were to draw a force diagram of the coffee, in this case, the earth is pulling the coffee down, of course. It's the force of the earth on the cup. And I don't know what the mass of the cup is, but let's just call it MC times that 10.0 newtons per kilogram. I should stop putting a multiplication dot in there because it looks like I'm dotting an I. Mass of the coffee times G. There is a support force from the roof called a normal force, perpendicular to the roof and equal to the force of the earth on the cup. That is the roof acting on the cup, and that's going to be equal to mcg also. I guess we'll just write that up there too because it's a flat surface. Now, somehow, if this thing is accelerating in this direction with the car, you actually have to have a force in that direction. What is the force that causes this thing to accelerate? Well, this is a case where friction is actually in the direction of motion. The static friction is going to pull this thing along. So picture if the top of the roof was the iciest ice you can imagine, as slick as possible. The coffee cup is at rest. The car underneath the coffee cup here, this big mass down here, pulls out. If this was a really icy surface, the cup would be like the table cloth trick where you pull the tablecloth out and everything stays in place, all the silverware stays there. The coffee cup would just stay in place because it has inertia. It doesn't want to move. The car would move underneath it and leave the coffee cup without any support. At some point after the roof passes underneath it, it would fall to the ground. So obviously there's some friction there, and the friction is actually in the direction of motion here. And it's static friction. Okay? You know that the equation for static friction is that its maximum amount is equal to mu(s) times the normal force. In this case, the roof on the cup, the roof on the cup. Better way to write that when we're talking about a generic normal force, I'll just use a big capital N. How about that? And in this case, that is that force right there. Now, the maximum acceleration this can have would be when the friction force is maxed out. So we're going to call this Fs max. So the greater that force, the greater the acceleration in that direction. So the maximum acceleration will occur when the static friction is maxed out. So the unbalanced force is equal to mass times acceleration. The unbalanced force in this case is this force of friction right here. So Fs max equals ma, mass of the cup times A. I'll put in there. Okay. Now I have an expression for the Fs max. It is mu(s) times the normal force mca. The normal force in this case is the force of the roof on the car. That's equal to mcg. So I'm going to substitute in for the normal force, mc times g equals mc times a. You can see, keep doing it, I don't know why. You can see, as in the last problem with the hockey puck, I've got MC on both sides. I can divide both sides by MC and cancel it out. Whatever you do to one side, you can do to the other. There it goes. It's gone. So it turns out you don't need to know the mass of the coffee cup to determine the acceleration. The only thing you need to know is the acceleration due to gravity, or we can think of it as the Earth's gravitational field strength in newtons per kilogram. Doesn't matter, it's 9.81 either way. Mu-s is 0.3 times 9.81 equals the acceleration. So 30% of 9.81 is 2.943 meters per second every second. That's the rate of acceleration. 2.3 meters per second every second. Let's see if that works. What did I just have? 2.94. Okay, they just did 2.9, 2 sig figs, okay? All right, so 2.9 is what they were actually looking for. What's the smallest amount of time in which a person can accelerate the car from rest to 22 meters per second and still keep the coffee cup on the roof? Not sure why they want to do this. Maybe they're doing a little experiment, but you're starting from rest. This is a kinematic problem if you didn't recognize it. You want to get to 22 meters per second. You know your acceleration now is 2.9 meters per second every second, and you're looking for a delta t. Okay? So the smallest amount of time would be at the maximum acceleration. Okay? We just figured out what the maximum acceleration was above. That is this number right here. So I like to use this version of that equation. You might remember this equation like that from the kinematic equations. This is the definition of acceleration. When you rearrange it, it looks like this equation down below here. So I'm just going to say my delta V is a positive 22 meters per second. The final minus the initial. Delta V is 22 from this. I divide by, I'm going to have to rearrange here. So I'll do it way over here on the left. A equals delta V over delta T. I multiply both sides by the delta T. Divide by the A. They switch places. Delta T equals delta V over A. We already said that was 22. My acceleration is 2.9. So let's get an answer. 7.6 to 2 sig figs is what I get. Let's see if that works, hopefully. All right. Well, we like to round the wrong way. I don't know why. Okay. Hope that helps. If you have any questions on Monday, feel free to see me. We'll do a little review session on Monday. And if you have any questions, you can come in early or after school on Monday. Okay? Have a nice weekend.